Hey good people, welcome back. In this video, you're going to learn how limits are used in calculus. I made this video to basically show you why we're learning about limits and how powerful they are, and they let you do a really cool thing, and we're going to see that in this video. Just to show you an example where you don't need to use limits, look at the example on the screen right now. The function f of x is equal to 0.2 multiplied by the absolute value of x. It's graphed below. Find the slope of the function when x is equal to 5. So we have to find the slope right here. And that's actually pretty easy because the slope's the same here as it is everywhere around it. We could just find two good points that intersect on the graph paper on the coordinate grid, and I'll use these two. And just going to use the regular slope formula, which is y2 minus y1 over x2 minus x1. Got my coordinates of my points, and I'm just going to plug that into the slope formula. The slope is equal to y2 minus y1 over x2 minus x1. So we have 2 divided by 10, which is otherwise known as 0.2. And we have our answer. When x is equal to 5, the slope of that function is equal to 0.2. But what if this was our function? Suppose we had the function f of x is equal to 0.1x squared plus 0.4x. We're asked to find the slope when x is equal to 8. That is going to be a little bit harder. It doesn't have the same slope at every point in this function. We can see that the steepness at this point, 8, is about this, right? And it looks more steep than it is at 3, for instance. If we were down here at 3, that has a different steepness. These two lines are not the same. So we actually use limits to answer this question. And this question is stated a little differently in calculus. Because we don't have this typical slope situation, they actually say, what is the instantaneous rate of change of the function when x is equal to 8? So we don't use the word slope, because slope is for lines. What is the instantaneous rate of change? That means, what is the rate of change at this exact spot? I graphed the function in GeoGebra, and here it is. And I constructed what's called a tangent, which is a line that touches this function at only one point. You could see that as I move this point, this tangent, along my function, the slope is changing the entire time. As x increases, the slope also increases, right? And we're supposed to figure out the exact slope at the point x equal to 8. To do that is a little tricky, and we're going to kind of draw a triangle and set up the slope formula based off that triangle. So here's my triangle. Let's say I was trying to find the slope between these 2 points. Let's call this first point the coordinates 8 comma whatever the function is evaluated at that point. We'll call it f of 8. So the coordinates of this point down here are 8 comma f of 8. And then let's say that this triangle has a horizontal length down here of some arbitrary letter. Let's call it A. That would make the x-coordinate of this point up here 8 plus A. Because all I did was I moved over A units from 8. And the y-coordinate of that point would be f of 8 plus A. Now, if I were going to use the slope formula to find the slope between these 2 points, I could get pretty close to the slope of the instantaneous rate of change at 8. But I'm not exactly there. But if I set up the slope formula nonetheless, it would look something like this. y2 minus y1 over x2 minus x1. What we want to do though is we want to take this triangle and make it smaller and smaller so that it actually approaches 8. I'll show you what I mean. Here's another diagram. We want to take this triangle here and make it smaller and smaller so that our tangent line, our instantaneous rate of change, is the slope between these 2 points. So what is A getting closer and closer to as I make this smaller and smaller? Hopefully you've realized this. A is getting closer and closer to 0. So we're actually finding the slope between these 2 points as A approaches 0. And I'm going to go ahead and do some calculations here. I already took the liberty of typing them in here so it's neat and organized for you so you can actually follow along. But we're going to evaluate the function, and instead of plugging in 8, we're plugging in 8 plus A. So I'm going to go right here in my function where the x is and replace that with 8 plus A. I'm also going to plug in a regular 8 into my function. I'm going to subtract those. That's it in the numerator here. So I plugged in 8 plus A into the function. I also plugged in 8, and then I'm subtracting them just like the slope formula tells me to do. In the denominator, it's a lot simpler. It's just 8 plus A, take away 8. All right, I'm just going to clean this up a little using algebra. That 8 plus A term right here, I'm just going to square that. And then I'm going to use the distributive property right here. And I'm going to square 8, which is 64, and multiply it by 0.1. I'm also going to multiply 0.4 by 8, which is 3.2. And here that's simplified a little bit more for you right here. Also in the denominator, 8 plus A subtract 8 is equal to just A. All right, a little bit more simplification. We're going to go ahead and distribute this 0.1 onto these 3 terms. And we're going to combine these 2 terms here. They add up to 9.6. Going to show you that. And we're going to keep going. We got to take these 2 terms here, combine them. Also, we're going to combine these 2 terms. 1.6a plus 0.4a is 2a. And you can see that this 9.6 here minus this 9.6, they're going to cancel one another out. And we can factor out something from both the numerator and the denominator, and then we're going to cancel that. So I factored out an a. Since that a and that a are both in the numerator and the denominator, and we know they're not equal to 0, we can just divide them. It's the limit as a approaches 0. It's not equal to 0, so we can just divide them and cancel them out. And now we have this. And I'm going to split this limit up into 2 different limits. And the limit as a approaches 0 of the function 2, there's nowhere to plug in a, so that's just equal to 2. And then we have to do the limit as a approaches 0 of the function 0.1a. Well, 0.1 times 0, or something getting closer and closer to 0, is going to get you closer and closer to 0. So this ends up just being 2 plus 0, which is 2. So what we can say is that the instantaneous rate of change of this function when x is equal to 8 is equal to 2. So the rate of change of the function for x equal to 8 is equal to 2. And you can actually kind of verify that by looking at this diagram here. Or rather this one. I made my triangle get smaller and smaller. This line's approaching that tangent line, the instantaneous rate of change of the function when x is equal to 8. And if you were to count up 2 units from here, 1 unit, 2 units, and then over 1 unit, it brings you back to that black line. And that shows you that the instantaneous rate of change of the function at that point is, in fact, equal to 2. So this is something that is done a lot in calculus, and luckily this result is generalized. You don't actually have to do this every time you want to find the derivative of a function. But this is how limits are used in calculus, and this is why we study them in pre-calc. Thank you for watching the video, and we are going to do some more basic evaluation of limits in this chapter. We won't really be doing something like this. Thank you for watching.